Hey there, class. Today we're going to talk about exploratory factor analysis, and I'm going to walk through an exploratory factor analysis in R with you. On Canvas, there's a lot of good resources. There are a lot of zip file with a lot of readings. It kind of follows along with chapter 4 in the FAIR text. There are some links here to some really good articles. I think this UCLA site, the Practical Literature Factor Analysis, is a great place, a good overview to read to start learning about exploratory factor analysis. Here's some more with an SPSS output. They kind of walk you through the output here. Here's an article where they use both exploratory and confirmatory factor analysis in R. And then in the zip files linked a lot of good readings. I would highly recommend this Beavers article to definitely read through it. This Beginner's Guide to Factor Analysis is another really good introduction. This Carpenter article is a really good intro into scale development. It also talks about factor analysis and how that fits in to the scale development process. And then the other articles are really about specific aspects. Here's some best practices, ideas on determining the number of factors to retain, another general overview of factor analysis. There's something about, writing up your factor analysis. And then I've also supplied just some older notes that I have on factor analysis that you can see there too. So be sure to look over all of those things. I also have on Canvas, you'll also find my R script file in there. There's an R markdown file. That's basically all of my R syntax and then the output all in one file. And then I also gave you a Stata do file to do kind of all the same things if you want to do it in Stata. All the syntax for SPSS are all in these like UCLA documents, so you have syntax for it as well. So let's open up RStudio. You'll need, if you haven't already, I think you already have the site package should already installed. You also need this. You also need these two other packages installed for this session. So the first time you do it, you have them installed on your computer. You don't have to do it again. We just need to call those packages. Open them up, and then let's open our data set. We're going to use that same SPSS anxiety questionnaire that we used in our last class assignment. So we'll go ahead and open it up. In the social sciences, we're often interested in trying to measure things we can't directly measure. Those are so-called latent variables. And factor analysis is a really technique we use for identifying groups or clusters of variables. It's really used to understand a set of variables. We typically use it when we're constructing a survey or questionnaire, and we're trying to measure some underlying construct. Factor analysis is also used to reduce a set of variables to a more manageable set. In psychometrics, we think of factor analysis as one way to help establish the validity of our instrument or test. So if our instrument is supposed to measure one construct, then all the variables should be highly correlated together. They should be highly correlated with each other. If our instruments, intended to measure 3 or 4 distinct concepts, then, items related to one construct should be highly correlated with each other and less correlated with the other construct. So, this really goes along with helping us establish the content or construct validity of our instrument. And, factor analysis is really just a data reduction technique that relies on the correlations in our data set. The existence of large correlations between a subset of variables would suggest that those variables are measuring aspects of the same underlying construct. So we're going to run through and kind of talk through kind of a factor analysis with this SPSS anxiety questionnaire data. So I'm going to use this data set also in our exploratory factor and our confirmatory factor analysis. And so since I don't want to run the EFA and the CFA on the exact same data set, so I'm going to split the sample in half. So first I'm going to get what half the sample size should be. We're going to set a random number seed, and then we're just going to split the data in half. And I'm going to save out onto Canvas. You'll have this SAQ, EFA, and CFA data set, so you'll have the exact same data set that I have. I've also saved them out as data files, so you'll have those as well. You can take these comments off to use it. So since we're going to be including all the variables in the data set in this factor analysis, we don't have to subset these data any. If you're not going to use all the variables in the data set, then you might need to create a new data set where we just take out the variables that we're going to use in the EFA. It just makes it work better in the package we're using. One of the first steps in a factor analysis is really to examine the correlation between the variables in the data set. We want our variables to be correlated with each other, but not too highly correlated. Typically, the recommendation, we're looking for correlations, greater than 0.3, but not like 0.9 to suggest, multilinearity or something. So, here's some syntax. We're going to just take our SPS anxiety questionnaire for the EFA and produce a correlation matrix, and then I want to round them off to 2 decimal places. Is what the next one does. And then we would typically look in this correlation matrix for variables that were highly correlated. If we noticed that a variable was weakly correlated with every other variable in the data set, say like 0.1 or 0.2 or lower, we might consider excluding that variable from the factor analysis. If we notice that 2 or 3 variables are highly correlated with each other, we might consider disregarding those variables. So we have a couple statistics that kind of help us with these decisions. So Bartlett's test of sphericity basically just tests whether the correlation matrix is an identity matrix. And by that we mean that all the variables are independent of each other. Basically, the correlation matrix would have 1 on all the diagonals and 0s on all the off diagonals, right? None of the variables are related to each other. So we can run it either with our raw data or our correlation matrix here. Notice we'll get the same thing. So the chi-square test is testing whether or not the correlation matrix is an identity matrix. We're rejecting that. We can also tell that by just looking at our correlation matrix. We saw some variables that were, pretty correlated with each other, that it didn't seem like it would be an identity matrix. We can also calculate the determinant of the matrix, and this is kind of gives us the opposite of what the Bartlett's test does. It's really a way to detect multilinearity, without getting into the math behind it, the determinant of the matrix you can kind of think of as like the area of the matrix. If you think of like a scatter plot, and all the variables, are plotted against these two, you can think of, the area of that as the determinant of the matrix. If all the variables were perfectly correlated, they'd all line up along a straight line, and there'd be no area in there. So the determinant would be of the matrix would be 0. So saying that it's a singular matrix. If the determinant range is between 1 and 0. If it's 1, it's saying all the variables are unrelated to each other. And if it's 0, it's saying that it's a singular matrix. So we want our variables to be correlated, but not too highly correlated. So the general rule of thumb is we want our determinant to be greater than 0.00001. We could run this, and we see down here, we said that that's true. So that's a good thing. We can also get a measure of the factor adequacy. So the KMO is the Kaiser-Meyer measure of sampling adequacy. I can't remember. The Beaver's article defines exactly what it is, but it's basically a measure of the shared variance in the items, or the proportion of variance among the variables that might be common variance. And we typically, we want our KMOs to be greater than 0.5. And I believe I shouldn't have closed that Beaver's article. She gives some good, you can see. So here we go. The Kaiser-Meyer-Olkins measure of sampling. So here's some general rules of thumb between, if our KMO is, 0.9 to 1, they say it's marvelous. 0.8 to 0.9, it's meritorious. It's just a way to suggest, the proportion of variance among all your variables that might be common variance. And what do I mean by that? So we kind of think of the total variance of a variable is made up of two components. It could either be common variance or unique variance. They talk about that. Okay, good. So we said the total variance in our variable, we can think of it as either being common variance or unique variance. The common variance is the variance that variable shares with other variables. And unique variance is variance that's specific just to that variable. And so we can think of unique variance as also into two parts, variance that's specific to that variable, and variance that's specific to that variable, but not really reliably so. And we call this error variance. So really in factor analysis, we're interested in the common variance among variables. Right? We're interested in finding common underlying dimensions in our data. So we're really mainly only interested in the common variance. When we run a factor analysis, we want to know how much of the variance in our data set is common. We really have two ways of doing this. We want to know how much of our variance in our data set is common variance. And so the way we do that is by running a factor analysis. So, typically we do this two different ways. One, we generally assume that we can do it. One way is what they do in principal component analysis, it assumes all the variance is common variance. So the communalities, that's what we call the common variance, called the unique variance. It's usually noted 8 squared. This one sometimes denoted u squared, or it's just 1 minus 8 squared, the uniqueness. So in principal component analysis, we assume that all the variance in the variables is common variance. So the communalities for all the variables is 1. So by making this assumption, we can then transpose the original data into linear combinations, and then we explain all the variance in the if we have 23 variables like in our data set, we can make 23 combinations of linear combinations of variables and explain all of the variance in the original data set. And that's what we do in principal component analysis. In factor analysis, we estimate the amount of common variance basically by using like the squared multiple correlation coefficient. So basically, we take each variable, say variable 1, and regress it on all of the other variables in the factor analysis. And so then basically the R squared from that model would give us our estimate of common variance. Once we do that, we can then identify which of the factors. We can identify the underlying factors that we've extracted, and then we can see how much of then we can recalculate our communalities to show how much of the proportion of variance that each one of those variables explains in that factor. So that's sort of the a real general overview of the difference between principal component analysis and factor analysis. So now that we've sort of determined that our data set seems pretty adequate to run a factor analysis, we're going to start by running a principal component analysis. I'm going to walk through a principal component analysis, then I'm going to show you some syntax for running a factor analysis as well. So we're going to use the psych package for this. You can, if you want help with the function, you can, highlight it, press F1, and you can get the help file for principal component analysis. So you can see the structure of the syntax, what each of the arguments mean, and then a little description about what's going on. So basically, we want to run a principal component analysis. Our data set is our SAQ EFA. I want to retain all of the factors, basically. And so what I'm telling it here, this is the number of factors you want to retain. So I could either type in 23, so that would be the number of variables in our data set, or I can have R count the number of variables in our data set. So basically that's what I'm telling it to, retain the number of factors. That's just the length of the data set. You can do that if you didn't know how the number of variables are in there, or you're too lazy to go in there and count it. So we can run our principal component analysis. So now we've created, and then we can call the analysis by just calling our PC1 function. Here's some syntax in here if you want to do it off the correlation matrix. You could do it either way, off of a matrix or a raw data set. So, I don't know why it keeps doing this to me. It's because in Zoom I have some, okay, here we go. You can't see some of the stuff on here, but it's got Zoom things down here at the bottom that's distracting me. So anyways, basically, here's the results from our principal component analysis. Uh, Here are our loadings for each of our variables. You can see each one of these here is principal component 1, 2, 3, 4, all the way 18, and then they'll go on down to 23. Right, we retained all of the components in our data set. You can see H2, remember that was how we denote our communality, so the proportion of common variance in the data set. Remember, principal component analysis starts off by assuming all of the variance is common variance. So you can see the communalities are all 1 for all of our variables, and the the uniqueness are all 0. These are, these are essentially 0. It's, if we've got 15 zeros in front of this too. It's just a rounding error here. We list our communalities and uniqueness here, and then we have our unrotated factor loadings. Currently this one isn't very interesting, and we're basically going to use this then to help determine how many factors do we need to extract. You can see, okay, down here. So first we have our table of our factor loadings. Then we scroll on down. We can get what are here labeled as sums of square loadings. Those are the eigenvalues associated with each factor, each component. And this basically represents the variance explained by that linear combination of variables. So here, component 1 explains 7.36 units of variance out of a possible 23 units of variance. So it explains, 32% of the variance in the data set. And notice the cumulative percent, we're explaining all of the variance. So principal components analysis will then explain all of the variance in our data set. We can also look on here and see, the first component explains a relatively large proportion of variance, and then it sort of tapers off after that. You see, one way of determining. So now, basically, the next step is we have to determine how many factors do we really want to extract out of this. One way of doing that, an easy kind of rule of thumb is we extract all components with eigenvalues greater than 1. So in this case, this would suggest we should extract 4 components. The fifth component is equal. We can say 4 or 5. If this one's exactly equal to 1, I'm going to say it needs to be greater than 1. So we're going to extract, may suggest extracting 4 components. This is known as Kaiser's rule. We can also view what's called a scree plot, where we plot the eigenvalues on the y-axis against a number of factors on the x-axis. And then we basically, on the scree plot, look for where the line sort of plateaus or starts to flatten off. Here's some syntax in R that will run a scree plot. So we're basically, we need to tell it. We need to tell it to plot. We want to plot from our first principal component analysis that we call PC1. The values. That's where it stores the eigenvalues. And then we want a line plot, type B. So we can see, typically the first component explains a lot of variance, and it drops on off after that. So we're really looking on here for where this plot tends to starts to flatten out. You might say starts to flatten out around the third or fourth component. We go first, second component, see a big drop. We see a good drop between the second and third. Another drop sort of parallel between the third and fourth, and then another little drop here between the fourth and fifth, and it really starts to flatten out. The scree plot, it's really a judgment call, where you start thinking that it starts to flatten out. Determining a way of determining the number of factors to extract from a factor analysis is really an ongoing problem in psychometrics. There's not one definitive way to do it. Probably currently the most popular ways are either Kaiser's rule or in the scree plot. We're going to show you just a few other ways of determining how to extract the number of factors. There's also an article on Canvas that discusses this in a little more detail too. Another cool way of doing this is what's called a parallel analysis. And so you can see up here, I sort of talk about it. We're basically extracting factors until the eigenvalues of the real data set are less than the corresponding eigenvalues of a random data set of a parallel size. So basically, we're going to compare the scree plot of our original data with a bunch of random permutations of data of our same size. And it's going to plot these on top of each other, and we're going to see sort of where the parallel line crosses. So the command in the psych package is EFA parallel. We basically give it our data set, and then so it has different factor analysis options. We're using a principal component analysis, and then the number of factors that you want to extract. I'm just going to tell it to do all of them again. And you can see down here the parallel analysis suggests we should extract 4 components. Here we're looking for, we want to extract all of the components above the line. So we looks like 1, 2, 3. The fourth one is right there above the line. We want to extract then 4 components is what it's suggested. You can also get it to, it'll also do different type of estimation methods too. You can look at the help menu for parallel analysis to see here, what type of extraction method you want it to use. You want to show eigenvalues for the principal components, principal axis factors, or both. There's another extraction method. There's several other ways. There's a very simple structure analysis. I'm not as familiar with all the details that go in to this analysis. It's basically looking at the complexity of each of the factors. And you can see here that the recommendations from the very simple structure analysis are all over the place. The very simple structure complexity of 1 suggests 1 factors. The VSS2 suggests 2 components. The BIC suggests 6 components. The sample size adjusted BIC suggests 7 components. So it's, like I said, it's all over the place. I think there's another in there, a map factor. Yes, yeah. Map achieves maximum with 1 factor. So you can kind of read up about some of these if you wanted to know more about them, but these are all just different ways of us trying to assess how many factors should we extract from our data. Another alternative is to just extract factors as long as they're interpretable. We can interpret what these factors actually mean. It also outputs a very simple a VSS very simple structures diagram. Basically, you look on here for where these achieve a maximum. You can see why they're all suggesting one. None of the other factors to retain the very simple structure fit isn't at. If it was, one was having its maximum was way up here, it would suggest 10 factors then there. So let's extract 4 components. The scree plot, the Kaiser value, the parallel analysis, really all suggested 4 components. And if we look up here, 4 components are explaining about 50% of the variability in the data. So let's extract 4 components and look at the results. So what you'll notice here is that the factor loadings, the eigenvalues, and the proportion of variance explained are all of the same as the first principal component analysis we ran. The main difference is the communalities and uniqueness have changed. And that's because we're not explaining all of the variance in these data. So you can see, here's our measure of the proportion of common variance associated with question 1. A portion of common variance associated with question 11. So you can see here our eigenvalues are the same, and so are the proportion of variance. Proportion of variance explained for each of the components. So another thing we can look at here is we'll know, well, how well then do these data, this extraction, this principal component analysis fit the observed data. And so we get like one model-based fit statistic. Here we have the fit based on the octagonal values, and typically we want this to be over 0.95. Ours is 0.96, showing that it's good fit. Another thing we can do is we can examine the residuals of this. So, we have our original data set with that original observed correlation matrix. We can also then have the relationship between the variables that is based off of these principal components. So we have that's what we call our reproduced correlation matrix. So these are the correlations that are suggested or reproduced by the principal component analysis. We could subtract those two, and that would be what we would call our residual correlations, right? Those would be the correlation, basically the unexplained variables, right? Basically, we want our residual correlations to be small, right? That the idea is that if our factor analysis explains all the relationships that the factors we've extracted have explained the relationships among all of the variables in the data set, then none of the variables should be related to each other. This will come in handy later when we talk about IRT. It's this idea of what they call local independence, that the only reason that these variables were related to each other is because they all shared this common variance, that they were all related to these underlying factors. And once we take into account that underlying factor, there's no more correlation among the variables. So that's the idea. That's kind of what the residuals are measuring. And so, if our factors or our components here are are doing a good job of explaining the relationship among the variables, then the residuals should be low. So we can actually look at then, just examine the residual correlation matrix. So we can use the factor residuals command here if you want the help items out of here. We can take the residual correlation, our original correlation matrix, and then the reproduced correlation matrix based on the loadings from our second principal component analysis. We're going to save that as a variable called residuals. We then only want to take the upper half of it, and we want to look for basically large residuals. And we're going to define a large residual as or correlation greater than 0.05, maybe. Field, you can see the citation down here, suggests if no more than 50% of the correlations are greater than 0.05, then you're probably okay. That then your factor analysis, the model that's defined in there, is doing a good job of explaining the interrelationship among the variables in that model. So here I basically just wrote some code that's going to then look for, and it's basically going to look for large residuals. Since here I'm just only looking at the upper half of the correlation matrix, and I want to take the absolute value of the residuals because the correlation can be positive or negative. And then I want to count the number of large residuals and then get the proportion of the total number of what that would be. So we had 90 residuals were greater than 0.05, and that ended up being around 36% of the residuals were greater than 0.05. I've seen also some people suggest you don't want them greater than 0.1, so we can get an estimate that way too. There's only about 22 variables that were greater than 0.1. It's only about 9%. So you can use your different rules of thumb there to examine. So I think our principal component analysis did a good job of explaining the interrelationship among variables in our original data set. You can get the another estimate of it, basically the root mean square residual. So we take the residual, square it, and take the average of it. So this is another measure of fit. And typically the suggestions are less than 0.08 is generally considered good fit. Less than 0.05 is really optimal. Ours is a little above 0.05, but it's probably okay. I think doesn't it report this? Yeah, it actually also reports it in the output for the principal component analysis, so you don't have to calculate it by hand, but we already had our residuals there that we could. We can also get a histogram of the residuals. Typically we want our residuals, are seen to be to be normally distributed. Histogram looks pretty normally distributed. So now that, we think core components does a good job of explaining our data set. But now what we want to do is what we call rotate the rotate the output or the loadings here. And basically what's happening in factor rotation is we're trying to make the factors more interpretable. These next two lines aren't going to work if you run this on yourself because I just have this diagram saved on my computer. But I did this to kind of give you an example of what's going on. So we have two factors here plotted on the y and x axis. This is factor 1, factor 2. And you can see these little blue dots, all line up along, typically define factor 1 and do a poor job of defining factor 2. And then same thing, the green dots are more along the factor 2 dimension. Basically, we're just taking the axes here and just tilting them one way. If it's an orthogonal rotation, we're tilting the same angle so that they're orthogonal or independent of each other. And then in an oblique rotation, we're allowing the factors to correlate so that here they're moving the same degree. Here, you see that the axes aren't moving towards the same degree. They're moving the same angle, but they're going towards each other. So that's the general idea of what we're talking about when we rotate our factor solution. We're basically doing a rotation just to make the factors more interpretable. You see when we move this line, the factors sort of line up along there a little bit better. There's several readings out there on Canvas that sort of talk about rotations and different kinds of orthogonal or oblique rotations. And this isn't a set, it's not really good defined rules, I would say, about, if you're an orthogonal rotation, you should, there's different kinds that are good in different types of situations. I think probably the most common orthogonal rotation would be a Wehrmacht's rotation. And so that's what we're going to run. We're just going to run that here. You can look at, we can go to the help menu and you can see all the different types of rotations that are available. Wehrmacht's, Quartermacht's, Promacht's, Obelman, Simplimacht's. So you can see different types of rotations that are available. And a lot of times it's like discipline specific too. About, a lot of people, typically use Wehrmacht's or typically use Obelman. Those are the two main ones I see. I think Wehrmacht's is probably the most popular orthogonal, and Obelman is probably the most common oblique rotation. So here's our output again with now that our factors are rotated. It's not that easy to read, so we can there's this print psych command in the psych package. We want to see the our third principal component run, and we only want to view the loadings if they're greater than 0.32. So it kind of disregards a lot of these small loadings. So you can see here, these question 1 and 2 don't load very strongly on component 1. And we can also tell we wanted to sort the loading. So I want the variable that loads the highest on that component at the top. It just makes the output easier to read. Nothing else changed in the output except that. But now we can see sort of what's going on here. So, rotating the factor structure, we can see here that, most of the variables load pretty highly on one component and either have, and mostly with weak cross loadings. By that I mean they're less than 0.4. There's a few here. Look, question 12 loads both on component 1 and 2, a little bit stronger on component 1. Same thing with questions 3, 16, 4, and 5 all have slight cross loadings. We might want to look at those, see what's going on. They're not too high and tend to load a little bit stronger on one component than the other. So I'm going to, for this example, just go with the variable, the component that the variable loads the strongest on. But this could be a situation where we might want to examine 12 or maybe even kick it out of the analysis and rerun our factor analysis to see if anything changes once we remove that item. But let's just sort of look at, now what we would do is we would pull up our questionnaire, that SPSS anxiety questionnaire, and we would look at all of these variables. So let's look at question 6, question 18. If we look at, component 1, a lot of these items seem to deal with computers. So question 6 is, I have little experience with computers. 18, SPSS always crashes when I try to use it. 13 is I worry I will cause irreparable damage because my incompetence with computers. All computers hate me. Computers have minds of their own. Computers are only useful for playing games. Computers are out to get me. So, some of these, they all kind of deal with computers. We might label this component, quote unquote, fear of computers, maybe is what we'll call it. We can look at component 2. All of these seem to relate to somehow to different aspects of statistics. So question 20, I can't sleep for thoughts of eigenvectors. I wake up under my duvet thinking I'm trapped under a normal distribution. Statistics make me cry. Standard deviations excite me. Notice that one has a negative sign for question 3. So that means it relates negatively with that factor. We'll need to take that into account later on. 16, I weep openly at the mention of central tendency. I dream that Pearson is attacking me with correlation coefficients. So we might call name this factor something like fear of statistics. Component 3 all seems to be related with math anxiety. I've never been good at math. I did badly at math in school. I slip into a coma whenever I see an equation. So maybe we'll call this one fear of mathematics. And then our fourth component here, question 9, my friends are better at statistics than me. My friends are better at SPSS than I am. If I'm good at statistics, people will think I'm a nerd. My friends think I'm stupid for not being able to cope with SPSS. Everybody looks at me when I use SPSS. All of these seem to be about what your peers might think of you. So maybe we'll call this one something like peer evaluation. So, this is typically the process we go through in a factor analysis. Once we've decided on the number of factors to extract, we've decided on an appropriate rotation method, then we go in and try to interpret the factors. That's why one of the suggested extraction method was interpret factors and retain the number of factors as long as they're interpretable here. So you can see all these items seem to relate to each other. So we try to think of like what construct then is it trying to measure, and you should have an idea of this in if our instrument here was supposed to measure, say, one concept. It was supposed to measure, and it was supposed to be called SPSS anxiety. Maybe we didn't do such a good job of measuring that, but maybe we designed this questionnaire to measure 4 different aspects of anxiety, right? And those would be, like anxiety over math, anxiety on overusing computers, anxiety over using statistics, anxiety over what your peers might think of you. Then maybe we did do a good job of measuring that. These results seem to suggest that this questionnaire is composed of these 4 subscales: fear of computers, fear of statistics, fear of math, and what our peers think of us, peer evaluation. So typically then the next step is to run a reliability analysis. And we sort of learned how to do this in our last lecture. To be able to use the reliability analysis in the psych function, we need to subset our data. So that's what I'm doing here. I'm creating new variables here called, computer fear, stat fear, math fear, peer eval, and I'm taking our data set and I'm subsetting it by the column number. It's really easy in this case because our questions are numbered questions 16, 18, 13, and that also corresponds to the column number. So I can just use that then to subset our data with. So let's just run that. And then we basically just use the psych package with the alpha command and then give it that new data set that we just created above. Remember that question 3 in the stat sphere, that it was standard deviations excite me loaded negatively. So we need to tell the alpha function to reverse code it. So we can do that a couple different ways. We can use the keys function and say to reverse code question 3, that variable. Or we could use the check keys command. The only thing about using the check keys is you want to make sure that's the only one that is reverse code. You just want to double check that it's doing it automatically. Whenever you get it to do it automatically, you want to just make sure it's doing it exactly what you want. So let's just run some of these. We can take a look at some of the reliabilities here. The raw alpha, standard out alpha is all pretty good, 0.85, 0.84, a tight confidence interval around it. Not surprising since we had about 1,000 people in the data set. We can see that deleting an item really doesn't improve the reliability that much. Maybe question 10, but it's not, only raising our alpha. Well, no, it doesn't actually raise our raw alpha at all, so nothing does here. You can see the inner item correlations. So remember, the R drop was the correlation between the item and the scale with that item removed from the scale. We want to see that these are all have a high correlation. This would be the mean of the scale if we drop that item, the standard deviation of the scale if we drop that item. We can compare that to the whole item scale statistics. And we can see if we had missing data. We can see the response frequency in each category and then the number missing there. Here's the Same thing for the statistics items. We want to make sure here question 3 was reverse coded. Alpha of 0.8, still pretty good. Removing any of the items doesn't really improve alpha. 20, you get the same alpha. We can look over here. You can see, it's it's not as highly correlated with the item scale, with the total scale when the item removed, but it's still got a decent correlation. We could always go back to our factor analysis here. Question 20 was actually the had the largest factor loading. So, I wouldn't, to me, this wouldn't suggest removing the item. If we did it with it just gave us a warning message that, if you use the check keys, it does it properly, but you just want to check to make sure it does. Let's run we can run the reliability analysis for the fear of math scale. Has a good reliability. Dropping any item doesn't change it. Really good correlations. Item total correlations there. Peer eval. Is the alpha for it is actually not so good here. Dropping any of the items doesn't really improve it. We might want to go back and think about, what's actually going on. We also want to make sure I grabbed all of the right, make sure we got the right. So it was 9, 22, 23, 2, and 19. Okay. Yeah, I mean, they had pretty decent factor loadings. They were all positive. It's the inter-items correlations just aren't very high. So we might, here we might consider, is this scale, useful for us or not? So those are basically the steps of running through a factor analysis. I've also presented some code down here. If you wanted to use an oblique rotation, you can print out your factors. If you wanted to run a factor analysis instead of a principal component analysis, the function is just FA, factor analysis. You can see the help function here. Here's a principal component analysis using principal axis factors with the Varimax rotation. Here's one using the minimum residual or unweighted least squares with a Promax rotation. And you can get the simplified solutions here. We look through here. They're basically aligning the same way. There's a lot of debate about whether you should run a principal component analysis or a factor analysis. Principal component analysis really isn't a factor analysis. A lot of the time, you come to the same conclusions no matter which one you run. If we look at both of these factor analysis, we're basically coming to the same conclusions we came to with the principal component analysis. All the items are loaded on all the same scales. One thing difference happening here, question 12 is loading basically the same on factor 1 and factor 2. What was that? The computer fear and statistics fear items. that we might want to consider dropping it from the analysis and rerunning the factor analysis. You can use the factor compare command to compare results between factor analyses. Here's a citation for using this. Basically a congruence coefficient of greater than 0.85 indicates a high degree of similarity between the factors, and greater than 0.95 indicates that the factors are virtually identical. We can see that there's a high degree of similarity between each one of here's our rotated components. 1 and our first factor, our second rotated component, and our second factor. So you can see very high degree of congruence between them. One thing I didn't really talk about, because we used an orthogonal rotation, is there's a difference between when you run an oblique rotation. Basically, one of the differences is in an orthogonal rotation, we're not allowing for correlations between our factors, and an oblique rotation allows for your factors to correlate to a degree. When that happens, there's a little bit of confusion between what's exactly the factor loadings. In an orthogonal rotation, since there's no correlation between the factors, this problem doesn't come up. But in an oblique rotation, it does. And typically, some programs output both what they call a pattern matrix and a structure matrix. R here only produces the pattern matrix, which can be thought of as the standardized regression coefficient between that item and the factor as the outcome. The structure matrix is basically the pattern matrix loadings times the correlations among the factors. And for some reason, there's not an easy way to get it out of R. You basically have to multiply those two matrices together, and that's what this syntax does for you. It multiplies the factor loadings times the correlations between the factors, and I'm rounding it off to 2 decimal places. And unfortunately, there's not a way to clean it up either. If you find something, let me know. But this would be the structure matrix. Most people will interpret the pattern matrix just because it's easier to interpret. It's probably a good practice to examine both the pattern and the structure matrix, make sure they agree with each other, especially when you're doing an oblique rotation. I have some notes on Canvas that talk about that in a little bit more detail. The final thing I wanted to show you on here is a really useful feature when you have ordinal data like we do in this instance. Remember these scales, remember we had really Likert scales. Well, let me see if I can pull up the SPSS. Yep, I was going to try to find we can look at the so a useful thing to do when you have ordinal type data, remember, so for this type, which happens a lot when you have using survey data, respondents are basically responding to whether they agree or disagree to this statement in this questionnaire. an assumption that, the Pearson's correlations are making, that the factor analysis is based off, remember, the Pearson's correlation matrix, is that the variables are measured on an interval ratio scale. Well, that's not really the case here. So, one solution to that that's been suggested is to, instead of factor analyzing the Pearson correlation matrix, is to factor analyze a polychloric correlation matrix. And so it's really easy to do in the psych package. You basically just add this command here that says to use the polychloric correlations. We can run this and we get very similar results. It takes it a minute to run because it takes a minute to calculate the polychloric correlations. You can see we actually get, our model-based fit statistics are actually a little bit better than what they were before. And our pattern matrix loadings is a lot cleaner this time. We still see question 12 having cross loadings that are pretty similar. And question 3 here is also having some questionable cross loadings. But it ends up being a much cleaner response. Some of these if you go and look at each of the factor loadings, some of them end up loading a little bit stronger. So that's another way you can do it that actually takes into account the ordinal nature of the data. You can also calculate what they call ordinal alphas using the polychloric correlation matrix. There's a good resource online here I've linked to. You can do that, where basically to run it in the psych package, we're going to do the basically just take the polychloric correlation here of that matrix, and then just run the alpha, telling it to use that correlation matrix. You can see actually the alpha gets a little bit higher than what it was before. We can see for the computer fear as well. We could rerun it. So you get all the same info. You just basically now take into account the ordinal nature of the variables. There's also some comments here talking about if you wanted to calculate factor scores, how you can do it with both the principal command and the factor analysis command. I've also there's also on Canvas for some syntax to run all the same thing in Stata. I don't go there and comment the Stata syntax as much as I did the R one, but you can sort of follow along the same way. I would definitely recommend reading the help menu for factor and then the post estimation commands for it as well. And you can see all the different kind of the same process we went through in this video. You kind of go through it with Stata as well. You can get the polychloric correlation matrix out of Stata. It takes it a little bit longer than R does, and you can factor analyze it. You can't, though, get the ordinal alphas, though, out of Stata. If you find out a way how, let me know. I wasn't able to figure that one out. Basically, that is our walkthrough of factor analysis in R. If you have any questions, please let me know, and post something, email me or post to the message board. I look forward to seeing you all in class. Thank you.